Hello everyone, good morning. Welcome back to COMP526. Let's jump right into it. Make yourself comfortable. Open the lecture back channel on Campus Wire for your questions or the audience Q&A on Slido. And let me know if anything's unclear, anything happened. I don't put up a slide for announcements. I'm almost done with marking all the lovely videos you made, but I will need 1 or 2 more days to finalize the marks, and then they will be available on Canvas. The only other thing really is the class tests this week and next week. Fridays is the deadline for both. One this week, one next week. So do that in case you haven't done it already. And we will have another programming puzzle upcoming. You've just finished one. In a couple of days, we'll release a new one that picks up on some new topics that we will discuss this week and next week. And yeah, then we're also slowly approaching the end of the term. But we're nicely on track. So with that, in case you don't have any other questions or discussion points, if you have, just put them in the Q&A, and I'll cover them when it's appropriate. If not, then I would continue where we left off, and that is in the middle of Lempel-Ziv-Welch. Let me see if I can get the green screen a bit nicer. Okay, better. Last time we talked about the Lempel-Ziv-Welch algorithm briefly already. So this was subsection 7.5. We're in the middle of the compression unit. And the goal of Lempel-Ziv-Welch is to compress text as illustrated in this little game using things that you've already seen, in particular when the text contains the same phrases again and again, copied or slightly modified. We want to achieve compression something like this, and the methods we've seen before wouldn't really cut it. Huffman encoding wouldn't really work that well because the character frequencies are not necessarily very uneven. And run length encoding would completely fail because natural language test hardly has strict repetitions of the same character. But Lempel-Ziv-Welch works fairly well. So it's a whole family of compression algorithms. I said that already. And this is where we left off. So the Lempel-Ziv-Welch algorithm is a variant of this family of compression methods, the Lempel-Ziv family, that is arguably the cleanest and nicest. It's also very practical. It used to be protected by a patent, so it was a bit controversial how to use it. It was legal trouble, but this is all gone and past now. The patent has expired because the method was old enough. So it's this is no longer an issue. I mentioned last time that it's a variable to fixed encoding. We take a variable length thing, part of the source text, and encode it with a fixed number of bits. And we'll use this typical choice of 12 bits, but that is a parameter you can tweak and play with. And that can be, this variable to fixed should be contrasted to Huffman, where it was fixed to variable. But really now, how do we do this? And that's the interesting part. So this is where you should wake up and pay close attention. We maintain a dictionary that is a collection of strings of phrases. These are all substrings of the text that we're compressing. At most 2 to the k entries. Initially, we will only have some entries for single characters from the source alphabet, but this dictionary will get filled over time. And the indices in the dictionary, the order in which we add things to the dictionary, that will be our code words. So we reserve the first code words, the first little sigma code words are assigned to the single characters of the alphabet. And all the other code words, so this is usually much smaller than 2 to the k. And all the other slots in the dictionary are reserved for phrases that we will add and that depend on the text. Now, how does this work to add new phrases to the dictionary? In Lempel-Ziv-Welch, it's done as follows. Whenever we encode a bit of the text, we add a new phrase. So each time we encode one thing, we also add one thing to the dictionary. And the rule is as follows. If we encode a substring x of s currently, so that's what's shown in the picture, the gray part is what we've already dealt with. That is encoded and done. Now I'm deciding, I'll tell you in a second how, that the next thing I encode is this substring x. Ban in this case. This is the next thing that we encode as one chunk, as one phrase. And the reason is it occurred already in the text earlier. What we do now, if we store such a phrase x, we add to the dictionary a phrase that is one character longer. We take the phrase we've just stored, ban, and we add one more character, which is this c, so in this banna. In this case. Okay, that's it. That's the rule. Whenever you store something, you take the next character that you could not at the moment already encode alongside with this, and you add this one character longer phrase to the dictionary. This new phrase is assigned the next free code word just by adding it at the end. That naturally happens. And that's the core of Lempel-Ziv-Welch. It's a fairly simple method. Now, I haven't told you yet how to select x, how to find x. The deal with that is you just check your dictionary and you find the longest thing you could match in your dictionary. And because we start with all the characters, you can always find such a match. We'll see an example where this becomes very clear. Just a little side remark. If we are implementing this, we would not store the string in the dictionary explicitly, but instead we would compress this in the following sense that whenever we used x, we know we have a code word for x. And so we can just store that code word and the new character, so we don't have to store very long strings in this dictionary. That's an implementation detail that we might not care at the moment so much for. Let's go through an example to see how this works and also see how we find x on an example. I said it's the longest string that you currently have in your dictionary that you find at this position. And let's practice that on an example. So here's our input, yo, you, your, yo, yo. And we will build the coded text one by one. We'll start, in this case, I'll just assume the full ASCII character set as the alphabet. Then we get a more realistic feel for how big the dictionary gets. We only use the ASCII set, not full Unicode. So the first part of our dictionary is already filled with all those individual characters. And I'm only listing those that occur in our example text. We include all of them here because we want a generic compression method that works for any text file, and not just for those that are comprised of these few letters. Okay, so what do we do first? We try to find the longest phrase in our dictionary that starts at the beginning of our text, of the uncoded part. At the moment, we haven't coded anything, so we're at the beginning. We only have single characters in our dictionary at the moment, so the longest thing we can find possibly is just the Y. And so we look up in the dictionary that this is 89. So we would first store 89 as our first code word, and then move on with the next phrase. But before we do that, we have to add a new phrase to the dictionary. Remember, whenever we encode something, we add a new phrase with the one more character added to it. So the first thing we add here is yo, because the next character is an O. Okay, that's how it goes. Next thing, we start again from here, read the longest thing we find in our dictionary. Well, we haven't seen so much, so that's just a single O. So we put that here, but then before we move on, also add the one longer, phrase is O with the exclamation mark. So that goes here and takes up the next slot in the dictionary. Okay, you see how this goes. As long as we haven't seen much, the method is fairly boring. We find the longest is the exclamation mark, single character. We add exclamation mark space to the dictionary as the next phrase. And we continue one more time. So here again, space. We haven't seen anything with space before. So the longest matches the single character. But we add space Y to the dictionary because that's the next character. Now things start to slightly become more interesting, because now we've actually seen yo before. So here we have to pick the longest. We want the longest match in the dictionary that we can find at this position, and that indeed is this yo. So here we use this new character, this new code word that stands for a phrase we haven't initially had in the dictionary, but it's a substring of our text. But we do the same thing. We store this phrase. It represents those two characters, yo, and we add u to the dictionary because that's the next character, yo plus one more character. All right, see how this goes and see how this eventually starts to save space as you see more and more of the text. If these things show up again, you will represent larger and larger parts with the same fixed length code words. All right, we go on. The U we haven't seen, so there's just the single character match, but we add U exclamation mark to the dictionary for later use. Now comes another interesting one. The exclamation mark space, we have seen that before. So we can use that, and there's no longer match, so that's the one we take. So we use this code and add a new entry to our dictionary where we have exclamation mark space, and then the next character is a Y again. Okay. Now things get again interesting. We have Y in the dictionary, we have YO in the dictionary, but we also have U in the dictionary. So here we can encode 3 letters with just one shot, and add the next character as a phrase to the dictionary. So here's your. All right. R we haven't seen, so that would be just the single character, but we add to the dictionary R space. Next thing, we've seen space Y, and that's the longest match, so we can encode that together and store space YO in the dictionary. Now I'll move myself to the other side. And then we're almost done. O, we have only seen O exclamation mark so far, so we are back to a single character, but we would add the OY for future use. And then here the YO we've seen, but not followed by an exclamation mark. So we've only got this one here, and we would add the other thing to the dictionary and finally encode the exclamation mark. So this is the final result. That's the encoded text for yo, you, your, yo, yo. And the decoding essentially works in the same way, where you have to replay this game. But first of all, if you have questions about the encoding part, this is a good point to discuss them. And if they only come up later, then we'll talk about them as they arise. Here's a more structured pseudocode, how this would be implemented. What I didn't talk about here is I did this manually, finding the longest match that's currently in our dictionary. But we know a good data structure for doing that, and that is a try. So for encoding, we definitely want to represent the dictionary as a try, because then you can start at the root and traverse down from the current position in the text onwards and see how far you can get. And as soon as there's no more outgoing arc with the right character, you know you're at the longest match. Now, unlike in the suffix tree applications and all examples of tries we've seen so far, here we actually want strings that are prefixes of each other. In fact, we will always have strings of single characters, so we must allow these. So here we would have space goes to one note, and that, for example, is labeled with 32. But we could also continue reading space Y, and I think that's the only character. So with space Y, we get to another note, 131, and there's also space YO, which gets us here, 137. So if we read in our text, suppose we're again at this position, we would now start traversing from the root downwards, reading characters as long as we can. So we can read the space, we can read the Y, and we can read the O, so we would stop at this position. But if we were, for example, suppose the text would continue with YI, then you would start reading the space and the Y, and then you would get stuck in this case. So you still need to have the shorter strings in your dictionary, because you sometimes need them and then extend the dictionary with the I with a new code word after you've added this. Okay, so that's the motivation here, and that's reflected in this code. So the code starts with initially an empty phrase. We have nothing seen. The coded text is also empty, and the dictionary is initialized as a try containing just the single character strings. The next free code word is always stored in K, and then we walk through the positions in the text. What's the next symbol of the text we have to encode? We get that symbol. Now we try to find XC in the dictionary. That essentially is walking down the try along the next character. If we can find this, then we keep that, but we're not necessarily done yet. We have to continue with the next character. So we continue traversing the try as long as we find matches. And the first time we fail to extend the current match, we don't find a longer string in the dictionary, that's when we get into this else branch. So here we append the code word for what we currently have read, X. That's the prefix, the phrase we found. And we add to the dictionary this one longer phrase, and we assign it the next free code word. That's exactly what we did in the example, a bit more structured. And if you use a try for the dictionary, this is also efficient. This traversal can always be done in constant time for the next character. All right. We can now encode with Lempel-Ziv-Welch and achieve great compression. But of course, a compression algorithm is only useful if we can also decode it. So in the next part, we will look at how to decode with Lempel-Ziv-Welch, how to decode the output of the encoder. As always, the two steps, encoding and decoding, they have to stay in sync. They have to replay the same game. And in this case, it's growing the dictionary. So whenever we decode something, we have to add the next bigger thing into the dictionary. And for decoding, this looks as follows. If we currently decoded X, this ban, that's the last thing we decoded. We know in the encoding step, when we encoded ban, we added ban plus the next character to the dictionary. So we also have to do this now. And so we take the next character from the next phrase. So we have to decode one more phrase before we can do this addition in the dictionary. So we decode the next phrase and take the first character. Then we know what the XC used to be in the encoding phase, and we can add that to the dictionary. So in a sense, we're lagging one step behind, but other than that, we're replaying the same game. We always have to deal with two phrases. We encode one, then we encode the next one, and that's when we can deal with the addition to the dictionary of the first phrase. So we only start adding to the dictionary after the second phrase is decoded. Let's see an example for how this works. And to make it a bit more fun, this is just showing the coded text, and you will only learn what the decoded text is as we go along to make this a little more interesting. So how should we start? Remember, we cannot add to the dictionary at the beginning. What we start with is a dictionary that's filled with the single character strings. So the first step must be a code word that's already in our dictionary. And in this case, we find it's a C. So the first character decodes to a C. So far, so good. Now we cannot handle the addition. When we encoded C, we added a new phrase to the dictionary. We cannot do that yet. We need the next character. So we decode the next phrase. That is the 65 goes to an A. And now we know C was followed by an A at the time of encoding. So CA was added as the first non-trivial phrase to the dictionary. And well, in the computer, it would be stored like this because we only have to represent the code word for this potentially long repeated thing. In this case, it's a single character, so it doesn't matter much, but just for completeness. But it's enough for us now to focus on this column. So we've added a new phrase to the dictionary and assigned it the next free code word 128. Now we decode the next thing. It's again a single character string found in the original dictionary. We add this. Now we know AN. After A, when we encoded this, it was followed by N. So we would have added AN to the dictionary. So we also have to do that now and assign it the next free code word. Let's continue. The same thing happens. We decode a single character and add this N space to the dictionary. And another time, and then things start to get interesting. So 66 is a B. The last character was a space. So space B was added at the time when the space was encoded. Okay. So far it was fairly boring. We only used the original dictionary, but now things become interesting because the next is a code word above 128. So here we use what we previously added to the dictionary. So the text so far reads like can ban. And we know the last phrase was a B. The first character from the new phrase is an A. So we would have added BA at the time of encoding to the dictionary. So we have to do that now as well. And so we move along and until we run into the situation that we're trying to use a code that is the next free one, and we don't know what it decodes to yet. So it seems like we're stuck in a dead end because we would need the information that the encoder put in after encoding this phrase, but we only get to that information after decoding this next phrase. So how can we get out of this problem? So that's a tricky situation that arises in Lempel-Ziv-Welch encoding. But fortunately, by looking very closely at this specific situation, we can actually resolve it. Let's zoom out a bit and see what happened. The reason why we ran into this problem is that the decoder is one step behind. The encoder encodes a phrase and then adds that phrase plus the next character to the dictionary. When we decode, we cannot do this because we don't know the next character yet. We have to wait for the next phrase to be decoded, and then we can add it to the dictionary. But it might occasionally happen that the phrase that we just inserted into the dictionary is the one that we use next in the encoding. And in that case, we're in this dead end. So we're trying to use a code that we're just about to build to insert into the dictionary. The good thing is, by looking carefully, this is something we can actually handle because we have all the information that we need. So we decode using k in the step that will define k. So we definitely add something to the dictionary after this step, and that would be the thing that we need. We know the last phrase x, but we don't know the next phrase y yet. We would need it to insert it into the dictionary and then use it immediately. But we have seen x, so that's where we decoded already. And the fact that the encoder uses the same phrase that we just create means that the last phrase plus the first character, that's the xc that we added, must also be what comes now, right? In the encoder, we used this Anna right after we inserted it. So Anna was the thing that we inserted, x plus the next character. And this is what we used, so we know that this is the same thing. And in particular, the first character here, the C, must actually match the first character of x. So we know this, that the next entry in the dictionary, xc, must actually be x followed by the first character in x. So it always has this little self-similarity in it because of this overlap. So this situation can arise. It can happen, as we've seen in the example, but if it arises, we actually know what to do. So it's not a problem after all. Here's the full code where you see how this is handled. And the interesting case is this, where we have to pull ourselves on our own bootstrap out of the swamp by using this special case. As you can see here, we use the first character of x. Maybe let me first finish the example, and then I'll show you the rest of the code in slightly more detail. So here again is our situation, and that's how it is resolved. At the point where we decode 133, we had not filled it yet. So that means we didn't know what this is. This was unclear, but we knew the last phrase was x, and that's indeed exactly the example that I drew here, also in this diagram. We knew x was an, so the first character of an is a, so the next phrase must have been Anna. So we can resolve this here, and we can also at the same time insert it into the dictionary, and everything's fine. And from then on, we can decode as usual. So let's briefly look again at the code, how this can be spelled out in a little more systematic way. Again, we need a proper data structure for the dictionary for this to be efficient. Unlike before where we used the try, here we actually need to find the meaning of a code word given the code word. And that is actually much easier. So we can just use an array where we use the index, the code word as an index, and then the entry in the array is just the phrase encoded as we've seen before. So we have similar variables as before. The next free code word, the first code word in the coded text that the next thing that we're decoding. And then the next phrase, and initially, well, we start with whatever the first phrase is. And then we walk through all the codes, the code words. We remember in X the last decoded phrase, so we always need X and Y, remember? Then we decode one more. That's the next code word from the coded text. And then there's two possibilities. If we're in this weird special situation that what we want to look up now is what we would fill after this step, we have this special bootstrap case, and we know what Y has to be. Otherwise, Y is just looked up in the dictionary. We know the next phrase then. And so in both cases, we know X and Y now. And so we can add Y to the decoded text. We know Y now, that's the next phrase we looked up. And we add the new thing to the dictionary, which is X plus the first character of Y. And this handles both cases now because we assigned Y in the right way. So that's all there is to Lempel-Ziv-Welch decoding. If you use an array here, it's very efficient. Decoding is a tiny bit more efficient than encoding, as we've seen before for Huffman. And indeed, this is very fast and can be implemented even in hardware devices. That's how this patent came first into existence. And in one way, in one variant or another, Lempel-Ziv-Welch is below all zip variants that are out there, and is very effective on many types of data. So before we discuss a little bit more what Lempel-Ziv-Welch is like, here's a fairly tricky question just to see if you're digesting this well. So this is tough, but it's an extreme case of a repetitive text. We have just n copies of A. And I'd like to know, what would Lempel-Ziv-Welch do on such an input? In a sense, it's the ultimate repetitive input. There's nothing more repetitive than just writing the same character over and over again. Remember, something like run length encoding would really compress this very well. And it's an interesting question to ask yourself, what would Lempel-Ziv-Welch behave like? What would happen? I didn't have an opening question today, so I don't know for how many people we're waiting today, but I would definitely hope for at least 20 or maybe 25 as usual. So I'll give you a little bit of time. It's also a question you actually have to think about a bit more. It might be more suited for a tutorial problem, but the tutorial was already full. And so I left it in the lecture. We have 17 people. $18, $20, $19. I'll wait a little more. Give you a second here. We're not in a big rush. So I'd love to see 25, that's for sure. And I'll explain what the correct answer is after we've seen the votes. Can we get 2 more people? Doesn't look like it. Oh, there they go. Of course. Great. So let's see. Let me log in the results. And indeed, the correct answer, the single correct answer is this last one. Is this, well, the last one on the first page. Square root of n. It's an interesting thing to look at. So let me move back to this. And you might wonder, why on earth square root of n? And to see this, you basically have to simulate the algorithm a little bit. So let's try to do this just on a small example, where I use some n's, some small n, and we'll look what happens. When we start, the dictionary only contains the single characters, so we would encode this as a phrase, and we would add AA to the dictionary. We would always be in this weird bootstrap case for this example. So we would always, in the decoding phase, we would always need this special case, but that's beside the point. The next thing we would read is AA, because that's in the dictionary, and we would insert AAA. So the next thing would be these 3 characters, and then, well, maybe I can add this. So after the 3, we would insert 4, and then we find this as the last phrase. So what you see is that with every phrase, the length of the phrase goes up by 1. So the total length of the string, if I have k phrases, say, with k phrases, I would go from length 1 up to length k, and I would sum up this. So n would be something like this, except for the last phrase, maybe. But let's suppose it's k full phrases. So you would have this sum, and as you know, this is quadratic. It's, well, we can say it precisely in this case. Not that it helps too much. K plus 1/2. So this is the famous little Gauss formula. And if you solve for k, I mean, this is essentially quadratic. So if you solve for k, this is square root n. You need square root n phrases to cover n copies of a. Might be interesting to remark that run length encoding got this log n, which is the number of bits you need to specify the length of the string. So that's it's hard to imagine that you can ever beat this log n here for that very special case. But Lempel-Ziv-Welch at least gets down to square root n, which is way, way better than linear. Whereas the best you could achieve with Huffman coding is n bits, right? So there's no way you get sublinear if you just use Huffman for individual symbols. Okay, cool. That was that question. So keep that in mind. This is essentially also the best case for Lempel-Ziv-Welch. You cannot really get better than square root n, but that is pretty good. So it's a decent best case. Run length encoding is really extreme. Good. Square root n can sometimes be achieved. Usually you don't quite get that, but you often get either a very good constant factor or sometimes even slightly sublinear. What is Lempel-Ziv-Welch good for? We've seen that we use as coded alphabet this this range 0 up to 2 to the d. Well, that's fine. That is binary, so you can use it as I presented it. But often you will not use all of the code words with equal frequency or equally likely. And then it might help to, as a second step after Lempel-Ziv-Welch, when you encode the phrases just using the dictionary index, it might be a smart idea to use a Huffman code on top of that, so that you don't just get the reduction from long phrases being represented by a fixed length thing, but also if phrases are used with different frequencies, you also exploit that. So that's a typical thing you will see again and again in compression. you chain these methods one after the other to improve compression and get the last little bit of redundancy squeezed out. What I didn't talk about so far is what do we do if the dictionary is full. I said we use a fixed length for the code words, but we also add another phrase when we encode it with one phrase. So we have to do something. Eventually the dictionary will be full, and then we have different options. We can actually decide that we then double the size of the dictionary, make D one bigger. That is a solution, but it means over the long term that your code words always get one bit longer, and maybe that is detrimental. Another idea is to just start from scratch, throw the dictionary away, start again with single characters, and go from there. That's nice because it limits the working memory that you need. Remember, for encoding and decoding, you have to keep the dictionary in main memory. And if you do this on a small device when streaming internet traffic, say, you might want to limit this. So that's something that's often done. A hack in between is to reserve a special code word that doesn't really encode anything in the text, but signals to the decoder, please now flush your dictionary and start from scratch. I did the same. So these are things you can play with. And the dictionary size is something, if you call a compression method a zip variant, they often allow you to say how big the dictionary should be. And that's a parameter you can play with. Okay, with the data structures that we've seen, we can do encoding and decoding in linear time, at least when the alphabet is constant, an assumption we often make for compression here. And so that is very fast, and it can also be done without seeing the entire text in advance. Remember, Huffman had this issue that you have to count the frequencies first. If we use Huffman for the dictionary codes, of course, we inherit this restriction. What is often done is you use Lempel-Ziv-Welch for a certain period of the text and for a certain block length, and then you start from scratch. That goes hand in hand with flushing the dictionary, for example. It does achieve very good compression for many typical kinds of data. So typical, I will always have these two examples, English language text or natural language text in a Western language, or biological sequences. And Lempel-Ziv-Welch turns out to work well for these, often achieving reductions of more than 1/2, of more than a factor 2. What is somewhat of a downside, at least from the typical implementations, if you fix the size of the dictionary, if there's a repetition, but that's very, very far spread out in the input text, you might not catch it because you flushed your dictionary before you could see it. Also, the square root n is I said is a decent lower bound, but it's not the best possible in some scenarios, as we've seen. So these are slight downsides, but it's a very solid method that is in wide use. I have a last slide on this part where we have a little comparison of these three methods that we've seen: Huffman codes, run length encoding, and Lempel-Ziv-Welch. Most of the things that are in here we already discussed when we were discussing these methods in more detail. And this also gives some typical applications and some numbers for English text, where you see Huffman is actually not too bad if you start with ASCII, but then Lempel-Ziv-Welch gets it down a good bit more. And yeah, here are some things where it's applied. I think Huffman codes are very ubiquitous in all kinds of formats, but just as a piece of it. So that's a little, with that little summary of the three main methods we've seen so far, I want to conclude this subsection. That looks like a good point for a little break. Maybe we'll just take 3 minutes. or 4 minutes. Continue at noon. Because then we'll slightly switch gears and look at text transformations. And maybe this is a good time for you to think about any questions you might have. Okay, see you in 3 minutes, guys. Use your break to, I don't know, go to the washroom, grab a new coffee. See you soon. Of course, any questions, pop them in the Q&A or the back channel. I'll be there. Now you can also hear me again. There, we're back. Oh, sorry. What I wanted to say is 11:50. This is not what I wanted. That's way too long. I somehow was under the impression that it's already 12. Okay, I hope no one is... I hope people are still here and will have noticed my mistake. I said 3 or 4 minutes and then I wrote nonsense. But I do like to continue, and there was one question on Slido that I want to discuss. So it's a bit small, but the question is, what do you do with the alphabet in encoding in general, I guess? And the answer to that one is really it depends on the application. Compression methods, the ideas are universal, but whenever you use them, you have to make conventions. There's typical programs for compression, like zip and all the friends and relatives. I think they just fix a byte as their unit, and then the 2 to the 8 different bit patterns, that is your alphabet. If you're working with text, maybe you want to restrict the character set a bit, but not usually. I mean, you're usually starting with files in one of the typical formats, and if it's text files, then maybe it's UTF-8, or maybe it's ASCII. And then you have this byte alignment. So one byte is a character. So the answer is either you make a convention and that convention is followed by encoder and decoder, or you have to send the alphabet, which is another option. I'm not aware of any methods that do this because there's usually better ways to achieve the same thing. For example, you could say the source alphabet is all thinkable characters, maybe Unicode in its entirety, but then you use a Huffman code. And then if the text is long enough, you have to send the Huffman code first. And that would come down to specifying the actual effective alphabet. But this is, for a very long text, is still more efficient. And is more general because you get the frequencies alongside with it. So it's a good question. In general, you have to make sure the alphabet is understood on both sides. I think that's the short answer. And that can mean you decide it's a shared thing, or it can mean you actually transmit it explicitly. Depending on the application, one or the other might make more sense. Okay, any other questions that we should discuss before we move to the next topic? But we can also discuss that later. In the third part of the compression unit, I want to talk about text transforms. These are things that don't by themselves compress text, but they help other compression methods. And one of them in particular is at the core of the modern achievements in compression and compressed data structures and text indexing. So it's definitely a very nice idea to hear about. So the idea of text transformations is to help compression methods overcome limitations. What we've seen so far is that certain methods can exploit certain types of redundancies. For run length encoding, these are long repeated runs of the same character. For Huffman, it's some characters that are very frequently used and others infrequently. And for Lempel-Ziv-Welch, if we have many repeated substrings not too far spread apart because of the dictionary size, then Lempel-Ziv-Welch does well. Unfortunately, methods can be very stupid whenever it goes a little bit beyond that. For example, Lempel-Ziv-Welch doesn't pick up any repetition if they're too distant. If the dictionary is already flushed, then we will not profit from these. And this is inherent. You can make the dictionary big, but then your code words are longer and you waste space on that side of things, unless you do extra steps after it. Or you make your dictionary small and then you miss out on this long distance repetitions. Huffman encoding totally ignores that the frequencies can be different in different parts of the text. That's particularly relevant for biological sequences. It just looks at the global average. How often does each character occur in the entire text? And so if you have local clusters where some characters are more likely than others, Huffman is totally blind to this. And run length encoding is very, very picky in that it only allows exact repetitions of the very same characters, and any slight disturbance completely throws it off. In particular, if you have a long repetition but it's alternating of two characters, run length encoding would completely fail and not achieve any compression. So text transformations have been invented to at least shrink these blind spots of the known compression methods. As I said, they don't themselves reduce the space usage at all. They might even make it bigger in some cases, but they make the existing redundancy, they transform existing redundancy in the text into a slightly different form. And that's often one that can be picked up by existing methods. And we'll see two examples of these. the first example is the move to front transformation. You might have seen move to front in a data structures class for self-adapting linear lists. If you haven't, it doesn't matter. That's where historically the idea came from, I think, but it doesn't really rely. What we will do doesn't rely on that use. So what is move to front? Suppose you have a linked list of items, and you repeatedly access items in that list. Then the linked list is not sorted, but you would like to profit from something like the same element is always accessed, or some elements are much more frequently accessed than other elements. And you don't know this information up front. So a simple heuristic, a simple idea for exploiting this is that whenever an element is accessed in this list, whenever you needed it, you move it to the front of the list. So a linked list, right, is just like this. And let's suppose here is your element x, and you access x now. So what you would take is, you take the entire list and leave everything unchanged except that you now take x out, move that to the front of the list. And because it's all pointered, you can do this without moving the other elements. And you shortcut the old pointer for x. So with changing 2 pointers, you can do this. The actual cost for the access is bigger than because you have to start from the beginning and walk along the list until you found x. But the cost of changing the list is really just 2 pointers. And there's some theory about this move to front heuristic that I won't get into here, but it's a cute topic in data structures that this heuristic is enough to learn the access probabilities of objects in an effective way in a specific sense. But let's leave it vague at this point. We will use here the same idea, but we abuse it for something very different. We will use a move to front list for the alphabet characters. And when we encode a character, we find it in the list, and we use as the code for this character the index in the list. How many positions did I have to walk back in the list? And we use its old position because after it was accessed, it always becomes the front of the list. But we can always store 0, then we can't decode. We cannot invert this transformation. But we can store the old position in the list and then do the update. So that means our code words now are integers from the same range as the alphabet is big. That's different from many of the other methods we've had. It's not a binary alphabet, but a much bigger one. And maybe if you think about this, maybe we'll do an example first. Okay, this is what it leads to. Let's see an example first. And to get started, I want you to practice the move to front rule itself. So you have a move to front list, as I just described it, where whenever you access something, you put it to the front. And so this is the current content. And now you access A. What is the list content after this single access? So this is just a, I abused the word cloud poll, but you can just type in the content of the queue of this move to front list. And I would say put spaces in between the characters. Okay, some answers are dropping in, and that seems fine to me. Maybe I'll give you a little bit more time, so we have a few more answers, and then I'll show the results. So remember, move to front works as follows. You access the element in the list, and then you take it out and put it in, well, you take it out and put it in front of the list. Let's see, at least 10. Okay. So we have a wild collection of ideas, and also of different spellings. That makes it a little challenging. But the fat one that was sent a couple of times is the correct one. It used to be XYZ ABC. Now we access A, so that means the A is moved to the front, but the rest stays the same. So we have A, X, Y, Z, and then BC is left as it was. Okay, so that's how move to front works. You, as I've had it in this tiny example here, this used to be X, Y, Z, and now I used X here again. I used X here instead of A, but it was A, B, C, and then after that you would have A, X, Y, Z, B, C. Another box for the C. Doesn't fit on the slide. That's how it works. Now, first question is, why should that be any good? Second question is, can we invert it? Can we get the original text back? The answer is yes in both cases. Let's first look at the second question. Okay, that doesn't work so well. I want to show the two pseudocodes just next to each other because they do the very same thing. And it's nice to see how they work in sync, because that makes it explicit how you can invert the move to front transform. So for encoding, we start with a list of all the characters in the not sure if this should be CS instead, because it's the source text. Well, we only have one alphabet, and the output alphabet is the numbers anyways. So we take a list containing the alphabet elements in sorted order. So this is important because we have to know how to start. Then for encoding, well, initially there's nothing encoded, so we start with the empty string for the coded text. Then we walk through the characters in the source text. That's the next character. We find the position of C in this list, so we walk through the list and check if that is the character we find. And then we store that position as the next code word. And finally, we move C to the front of the list, and we repeat. We do the same thing in the decoding. I have to fix this here. So decoding starts building the same list, the alphabet in sorted order. Initially, the decoded text is empty. We walk through all the coded symbols, which are the numbers, and then we find the pth position in the list and return that. Okay. And then again, we do the same move to front. So you see how these are synced up. They start with the same list, and they always change the same list. They change the list in the same way, and they extract the characters in the same way. So by putting the code next to each other like this, it becomes obvious that they do the very same thing. So encoding goes from characters to numbers, decoding goes from numbers to characters, but they always make sure that these two things remain in sync by keeping the move to front list in sync. I have a small example for you on this, but I want to go through this fairly quickly because I think it's fairly easy. Here's the alphabet sorted initially in the list. Now, you start with I, you find it in the list. It has position 8, so the first output character is 8. And now you have to move I to the front of the list. So you see how these all jump one position to the right, and I jumps to the beginning, right? I jumps to the beginning, then comes A, B, C, D, E, and so on, up to H. Next character we want to encode is N. It's found at position 13, so we output 13 as the next code word. And again, move N to the front, and everything between the front and N, one position to the right. So one more time, loop, there it moves over. The next character is E, so we find it at position 6, store the 6, then move E to the front, gives you this list, and so on and so forth. I think the concept is probably clear. So you can go through this in detail if you feel like it, and well, double check if you arrive at the same result. Now, an interesting observation is what happens in this transformation with certain features in the input text. For example, when the input source text has a run of same characters, like here, what does that correspond to in the coded text? And what does the run in the coded text mean for the source text? That's two interesting questions to think about. I think I should put these on top of each other so that this becomes more visible, but the first question is really a run of characters in the source text means after the first character from the run, we have that character at position 0. So all remaining characters from the run will have a 0, will be represented by zeros. So we find zeros in the coded text whenever there were repeated characters. And what does a run of a certain digit in the coded text mean? For example, here, the 3s. Those are these 3 characters. They're not the same. So what does that mean? Well, it means that, maybe let me do this in a different color. Different color. Run in C. It maps to these 3 characters. And you find 3 positions back, the same substring occurs. So runs in the coded text mean there was a repetition in the source text. And that's a pretty neat result because we know how to exploit runs in the coded text with run length encoding. And we didn't know, well, at least not with run length encoding, how to handle repetitions of this kind. Lempel-Ziv-Welch would have been able to pick this up if it's short distance, but that gives you a first idea why move to front might be useful. As I mentioned before, move to front doesn't really compress. That's why it's called a text transformation. It doesn't really make the text itself shorter, but it allows for other methods to work better. It's basically used as part of a longer pipeline. In isolation, it doesn't really do a lot of good. The code words that come out of the move to front transform itself have to be represented in binary somehow. You could use the Elias gamma code that we used in run length encoding. And that makes sense because smaller numbers get shorter code words in that code. If we have local clusters of characters, that will lead to small numbers after the move to front transformation. So that can work well. And the other option is, of course, a Huffman code. Then you would have to do the 2 passes, but it achieves better compression. But the most striking reason why we want the move to front transformation is actually only clear after we talked about the next transformation, because those 2 in combination are the really effective compression methods. Any questions about move to front? If not, then I'd like to move on and try to get at least the most part from this section covered. In this last subsection from the compression chapter, I want to talk about the Burrows-Wheeler transform. That's the most sophisticated text transform that we will cover. And again, it will not by itself make the text compressible, but it makes redundancies in the text explicit and then allows other compression methods to work much more effectively. And that makes the Burrows-Wheeler transform the core ingredient for modern compression, both for static compression, where you compress and decompress, and for data structures where you work on the compressed representations. For both, the Burrows-Wheeler transform has been instrumental. And it's also a beautiful theoretical idea. Maybe also as a historical side remark, when the transform was first thought of, it was deemed impractical because it needs a lot of extra memory. It needs to have the text all in main memory. And so it was deemed impractical and not pursued. And only much later it was published when people realized that it is practical with the improvements of hardware and memory sizes. So this also tells a story about algorithms in general. Sometimes a sophisticated idea looks impractical at the time you think of it, but it's still worth exploring because it might become practical in the near future. And this is what definitely happened to the Burrows-Wheeler transform. What is it, the Burrows-Wheeler transform, the BWT? It's a way to scramble around the text characters. It uses the same letters as the source text, but in a different order. And that order is specifically chosen to help compression, to help other compression methods. We'll come to that in a second. A downside from that is that it needs the entire text to compute. You need the entire text to compute the BWT. And maybe what convinces you most is if you take the BWT, follow it by move to front, then run length encoding, and then Huffman at the end. That is at the core what is behind the bzip program. And that achieves the best compression we know for English text. I've shown you here, this is just the English Bible. So that's some 4 megabytes. That's all there is to it if you store it in plain text. If you use gzip, the GNU zip, you get it down by a factor of 4, which is not bad. 7-zip, which is often deemed the most effective general compression method, is much better than GNU zip, gets it down to that. But bzip actually beats 7-zip for text. Without discussing this much further, it shows that having the right conceptual ideas achieves good results also in practice. And that's even though these two are very highly engineered, this comparatively simple method beats them by using the appropriate tools. To be fair, I should mention here that bzip tends to be slower than the other methods. So there's a trade-off to be made between the time it needs to compress and decompress and the compression ratio. But if the actual compression ratio is what you're after, then bzip is very solid. Okay, I finally want to tell you what the BWT is. For telling you that, I need to introduce a cyclic shift of a string. That's a simple concept. If you have a text T, a cyclic shift just means you start in a different position and wrap around. So if you write the string like this on a circle, time flies quickly, then originally this was the starting position. I can move the starting position to some other point, and then I start reading the text from here. That's a cyclic shift. cyclic because it's on the circle. I think it's intuitive enough. And so one cyclic shift of this string is flies quickly time. Not sure if that's a sensible sentence, but it's the best example I could come up with. If we add an end of word character, and you're by now familiar with these, then the cyclic shifts become invertible. I can always continue shifting until the $sign is at the last position. So that's a convenient convention, and we will use this for BWT as well. So take a text, append the dollar character, and then the Burrows-Wheeler transform works as follows. You take all cyclic shifts of your text with the $sign at the end. You sort all those cyclic shifts lexicographically, and then you take in that sorted list the last column top to down and read down these characters. And that gives you the Burrows-Wheeler transform of the text. This, I'm sure, sounds crazy. And it kind of is, but it's magic. No, it's a smart trick and a smart way to exploit redundancies, but I'll show you in a second. Let's first see an example on how this works. So here's a sample text that we will see a couple of times over the next slides. Alf eats alfalfa. That's some sort of grain or so, some plant. So it's an actual valid English text, in case you care. For the BWT, this is not the main point. What we need is all the cyclic shifts. So this is the text with the dollar at the end. You get all cyclic shifts by starting at a certain position and then starting from the beginning modulo the length of the text again. So these are all the cyclic shifts, right? Starting at all positions, and you see visually how you just shift things by one character to the left when you move down one line. Now we lexicographically sort these, and that gets us this list. So these are the same strings, but now sorted alphabetically. So the dollar comes first. That's our convention from Unit 6 as well. Then space comes before all the alphabet characters. So if you look at this list, this is always sorted, right? Goes from small to big. But the only thing we really take from this picture is the last column of this sorted list. So you read this column top down, and that is the Burrows-Wheeler transform of this text. And if you look at this gibberish, it's not at all recognizable where this came from. It looks quite different and quite weird. You might notice that there's these runs of characters, and that is a typical thing. It's definitely something that happens when the text is repetitive, and that will be what we're after. But the way we got to this BWT might still sound fairly wild. Now, I want to get you a little bit thinking, and in case this wasn't already on your mind, I want you to think about the relation between BWT and suffix arrays. So the concrete question is, we had the suffix array L, the leaf array, right? Well, the sorted suffixes of a text, take all the suffixes of a text and sort them. That's L, and we have the text, and we have the BWT and the text. And so the question is, if you have either combination of either L or B and the text, is it easy for you to determine what the other is? And yeah, I'd like to see a few more answers, and maybe up to 20. Then I'd like to show the results and move on. 17, 19. Okay, one more. We can get one more, please. And I think it's looking good. Yeah, so there we are. And let me lock that in. The majority got it right. As you probably noticed from this picture, I'll show you a better picture here. If you take cyclic shifts and sort them, you never really compare beyond the dollar character, because the cyclic shifts, these are all the different cyclic shifts. Dollar occurs only in one position. You never have a cyclic shift where the dollar occurs at the same position. You never have an equal there. So any comparison between cyclic shifts will have the same outcome as if you ignored the gray part and just looked at the suffix starting at the same position. Okay, so sorting cyclic shifts is the very same task as sorting suffixes. And that, of course, means if you have the suffix array and the text, then you know the sorted order. The only thing you need then is to jump to this last column, but that's always the character that precedes this index. So if you have, for example, here, if we know that this is the starting position, this A is the, what is it? It's actually the first character in the text. That's let's not use this example, that's degenerate. But this one, this is the suffix that starts at the second to last character. So what's the last character in this column here? That's whatever is preceding this. So if you just take I-1 and access the text character at that position, you get the BWT. So it's easy to compute the BWT from the suffix array and the text. It's possible, well, it's always possible because you have the text. But A is more challenging because the BWT loses the information about where the text started. It only keeps this last character, the last column character, and that alone doesn't make it very obvious how to compute it. There are more sophisticated methods with a little bit of insight that make this possible, but it's not easily possible. Good, so that connection gives us an efficient way to compute the Burroughs-Wheeler transform, because sorting cyclic shifts is the same as sorting suffixes, and we know how to sort suffixes. All right, and here's the formula more explicitly that shows you how to get the character, how to compute B from L in the text. Here the text is called S, but other than that, it's the same thing. Okay, that's how we can find the BWT. That's the first good thing. We can efficiently compute it. The next question is, why is this any interesting? Why does the BWT help us in compression? And for that, I think I need here the example. What the BWT does is it groups characters by context, namely by what follows them. So for example, we have a context here. LF is repeated here in these positions. And you see it's grouping these A's together into a run. And the reason is that we have this ALF 3 times, and it's contiguous here. So all the occurrences of LF in the text are actually preceded by an A. If there were other things that precede LF, they would also be in this little contiguous range. So we group characters by what follows, and that means if there's redundancy in terms of, I don't know, TH is often followed by E, the BWT is able to pick that up. Well, if there's other characters that can come after TH, like A, then the BWT is still able to make that more effective by leading to local clusters of characters. So it groups characters together by what can come after them. And if let's do another example here. If that is my example, then in English you can have a T in front of it or an S in front of it, but you probably don't find an X in front of it very often. So in the region where you have HA in this sorted range in the front rows, the last row would contain S's and T's a lot, but no X's. And that's what I mean by local clusters here. And finally, if you have repeated substrings in S, you usually also get runs of characters in the Burgers-Wheeler transform, as in this example. So that's what I already said here. Alf is repeated 3 times in Alf eats Alf alpha. And that repetition in the BWT leads to runs of characters. So this was only a vague intuition why the BWT will be helpful for compression, but it should give you at least some indication. I want to show this on a bigger example as well. So here we have this text, have, had, hadn't, hasn't, haven't, has, what. And if you look at the BWT, you find there's a lot of characters that are repeated. And if you then apply the move to front transform on the BWT, let's remember what bzip does, then you find a lot of zeros in the move to front transform of the BWT. Yeah, let me ask this question, and then that's the last thing for today. So a little just thinking from first principles on this example. We have this example text, have, had, hadn't, hasn't, haven't, has, what, and it's BWT, and it contains this long run of H's, like this one. Not quite as long, but this. What does that really tell us? How can we argue that this is occurring as a run of how can we explain this run of H's? And be very careful about how to argue about this, because several of these answers make sense, but they're not necessarily all correct. And again, so I left this here because it's insightful to look at this run of H's here. It's the same here. And because we're already at 12:30 and I have a follow-up meeting right after this, I think I'll have to close the vote now so that I can at least briefly discuss the result as well. So I marked essentially only this single answer as correct. Let me lock it now. And let's move back to this. So I said the correct answer is that all A's are preceded by an H. And that's the statement that we have all the A's in the text here. They're necessarily together because we sort the suffixes or sort the cyclic shifts. And if you check what comes before those, all H's here are before this A. So there's no other character in this example text that precedes the letter A. And that is guaranteed to give us a run of H's of the number of the length as many A's as we have. We will have a run of H's. Of course, it's also true that this text has long repeated parts. In particular, it has these repeated parts, space HA, space HA, space HA, space HA, quite a couple of these. And you can trace where they end up in the BWT. They also give rise to runs in the BWT, or at least local clusters, but not always contiguous runs. For example, here, if you look at this, this is all, maybe zooming, oops, that was a bad idea. All these are all the suffixes starting with HA, but not all of them are preceded by a space. There's also these two other cases. So even though you have this repetition, you don't get a clean run, you just get a local cluster of the space in the BWT. All right. We're over time, so I'll stop here and we'll continue tomorrow. Well, we still have to see that's what I wanted. So I've hopefully convinced you now that the BWT is an interesting transformation. I haven't shown you how to invert it. And if you think about sorting, usually loses information. If you sort a list, you can't go back to the original state of the list before the sort. With the BWT, I promise you that this is actually possible, but this is not completely obvious if you first see this definition. So stay tuned. We'll discuss this then tomorrow. Bye for now. And I'll have to skip the social today because I have to jump right into another meeting. Sorry for that, but we can do the chat tomorrow. And see you tomorrow at 11 a.m. And I think that's it. See you tomorrow. Have a good day. Bye for now.